Hey everyone, welcome to the next talk in the GPU computing seminar series. I'm Will Landau with the Department of Statistics at Iowa State, and this is actually not the main talk that I gave today. The video didn't work, it didn't record audio for some reason, and so I've already given the talk, but I'm giving it again because I want to make sure I'm giving it again as a screencast because I want to make sure that this gets online, because I'm going to talk about the Thrust library, and it's one of my favorite libraries, and it's one of the most useful, so I want to make sure that information gets out there. So I'm going to get us started. I'm going to jump start us with some code, and then I'm going to talk more in depth about three key ideas in the Thrust library. They're iterators, containers, and algorithms. And let's plunge right in. So Thrust is the CUDA analog of the standard template library in C++. So the standard template library has a bunch of data storage classes and algorithms to crunch numbers on those storage classes, and it's really useful, and it's in C++, but unfortunately it's not GPU accelerated. But CUDA has an analog of the STL, which is Thrust, which takes all out of those algorithms and accelerates them and takes care of a bunch of other features too. So the data structures are all stored dynamically. That means they're either allocated with malloc or CUDA malloc, so you can change the size of the data structures on the fly during runtime and not compilation time. And really conveniently, Thrust encapsulates a lot of this GPU-CPU communication. So all your CUDA mem copies are taken care of, and you'll see that in a bit. You also don't have to, and also the parallelism under the hood is managed. So to use Thrust algorithms, you don't have to write your own kernels. Those kernels are built in to the Thrust library, and you don't need to worry about how many blocks or threads per block you need. The Thrust algorithms take care of all of that. And the algorithms include sorts and reductions and a whole bunch of other neat things that are very common and you don't necessarily want to implement yourself. Thrust came from Comrade, which is its direct predecessor, which is has been officially out of use since 2009. Thrust took over, and it's maintained primarily by these two guys, Jared Hoberock and Nathan Bell from NVIDIA. They put together also a web tutorial of Thrust, and I highly recommend you check that out because it's a much better talk than this one that I'm giving now. I'm giving it because I'm trying to tailor this stuff to statisticians, but if you really want to know what's going on with Thrust very well, you should check out their webinar. They did a much better job than I will. So let's plunge right into some code. So this looks a lot like C++. You see this include IOStream. That's because CUDA C is not only just CUDA C, it's CUDA C++ as well. So we have a lot of C++ capabilities if you use the NVIDIA C compiler. That's the first thing to note. Second, Thrust has a lot of header files. Thrust, you don't need to link Thrust at compilation, but you do need to include a lot of these header files for whatever data structures or algorithms you want to use. So I'm using a host vector and a device vector, so I'm including both of those libraries up top here. Now I'm going to start by creating a host vector. That's a vector, which is an array with a bunch of other stuff that I'm going to go over. And I'm going to create it as a vector of ints. Its name is going to be h, and it's going to have 4 elements. That's the syntax. You can reference elements of h as you would any other C or C++ array. That's really convenient. But h, like I said, is not only an array, it's a vector, so it has a bunch of other things. So it has member functions like size. So you can call h.size, and you can print out how many elements there are in h. And notice this cout and these double angle brackets, those are C++ syntax. So if you aren't familiar with this syntax, I highly recommend checking out a book by Walter Savish called Absolute C++. I read it cover to cover when I was in undergrad. It was my first C++ class, and it did me a world of good. That book is excellent. So I highly recommend you check that out if you struggle or you're tripped up by this C++ syntax. Anyway, so I can print out the elements of h and the size of h this way. There are a bunch of other functions besides size, other member functions. For example, if I want h to just have the first two elements, if I want to just take the first two elements and call that h, I can use the resize member function. I can also create device vectors. So just like I declared host vector h up here, I can declare a device vector d. So it's called d. I could have put parentheses 4 if I wanted it to just be any device vector with 4 elements. When I do device vector d equals h, it's automatically doing the CUDA mem copies and CUDA mallocs that I need to create d and to copy all the elements of h into d. So this equal sign is this assignment operator is overloaded, and that's really cool because you can do all this copying and allocating just in one line. That's part of the power of thrust. That equal sign is overloaded. You don't even need to think about what's going on between the GPU and the CPU. It takes care of all that for you. And here's the output just to make sure it works. Notice you don't need to link any external libraries. Its thrust is already built into CUDA, which is really nice. Like I said, all this stuff is taken care of for you. The equal sign is overloaded conveniently. Now a bit about namespaces. So this thrust : and standard : clarify the namespace that you're using. So every library has a namespace, which is a collection of bindings, which less formally is a collection of assignments of function names to the functions themselves and data structures to and data types to their definitions. And so when you have conflicts in names, in the thrust library you have a definition of the function copy, and in the standard library, in the C++ standard library, you also have a definition of the function copy. Which one do you use? Well, it can be ambiguous at times, but if you want to use thrust's version of copy, you proceed it with thrust : copy, and likewise for standard. Whenever you use thrust, I recommend always using that thrust : at the beginning of all your functions that you take out of thrust to avoid the ambiguity in those conflicts. Hopefully the compiler will warn you about them, but not always. The errors may go silent. You really need to be careful. Like I said, this is syntactic sugar for printf. You can do everything in printf if you want to, if you like that better, if it's more comfortable. Here's another example. So I have a device vector of this is another example of just playing with code. It's not really doing anything significant, but you do get your feet wet and you do sort of see what the syntax is like and what it does and how to play with it yourself. So I create a device vector of ints, and that's going to have 10 elements, each with the value 1. Now dbegin and dbegin you can think of is it's called an iterator. For now you can think of it as a pointer to the beginning of d, and then dbegin plus 7 is 7 elements down. So you can think of these as pointers for now. They're really iterators, and I'm going to go over formally what iterators are in a few slides. Sorry about the resizing thing. That was an accident. So in thrust fill, what that does is it says, well, I'll look at the element pointed to by here, by this guy, and all the elements up to the element pointing to by this guy, and I'm going to set them to this value, which happens to be 9. So I'm going to set the first 7 elements of D equal to 9. I'm going to create a host vector just for fun, Again, a host vector with basic type int. All the elements are in it are ints. And I'm going to create it out of the first 5 elements of my device vector D. So that's dbegin to dbegin plus 5. It's going to copy those 5 elements out of the GPU, because remember, device vectors live on the GPU. It copies all those elements from the GPU to the CPU, stores it in the first 5 elements of H. I can take those elements of H, I can go from the beginning of H to the end of H. That's going to be 5 elements down because I initialized H with 5 elements. And what thrust sequence does is it initializes the elements of H to the sequence of numbers from 0 to however many elements there are minus 1. So H now has a 5-element sequence. I copy all of H from beginning to end back to D, beginning at this pointer, or this iterator, dbegin. I'm going to use thrust copy for that. It's exactly what it looks like. Copies the elements from here to here into this vector starting here. Alright, and that's all that program does, and you can check that this is the correct output when you compile and run. So thrust copy, like I said, sort of, copies a section of one vector into another vector. Thrust fill is another function for assignment. It sets a range of elements to some fixed value. Then you got thrust sequence, which is a little bit more fancy. You get a sequence of values assigned to a vector, a section of a vector. And those are some simple assignment functions that you get for free. And now I mentioned this thing called vectors. What are vectors? Vectors are kind of storage class. And you declare vectors. I should say vectors are kind of storage template class. A vector isn't exactly a class. It's a template class. What I do is to create one, I call thrust device vector angle brackets, and T is some type, and D is the name of the device vector. Now, what's really important to note here is, well, a device vector is not actually a class, it's a template, so it's actually a set of classes. If I give you a data type T, that defines a class. So this whole thing denotes a class given T, but this template device vector is really a set of classes, and you get one class for each data type. And that's sort of the idea behind the standard template library as well. Sometimes you want to use ints, sometimes you want to use floats or doubles or even complex numbers or what have you. And you don't want to redefine all these classes for those different basic data types. And that's where templates come in. And if you want to know more about that paradigm, you can look at the standard template library in C++. That may make more sense because there's more documentation on STL than there is on Thrust. That might be a good place to start. If the people who develop Thrust basically assume that you know STL, and the transition would be relatively smooth. There are also host vectors. So device vectors, I don't know if I said this explicitly, I should have, but device vectors are on the GPU. They're stored in the GPU, and they can be called with GPU parallel algorithms. The analogous declaration is host vector. So a host vector is exactly what it sounds like. It's a vector, but instead of being stored on the device, it's stored on the CPU. And so the algorithms that you call on it won't be GPU accelerated like they would be on the device vector. So in a vector, like I said, a vector is like an array, but with some other fancy things attached to it. And in addition to that array, the fancy things are called iterators. And you get dbegin and dend as your iterators. Well, what's an iterator? I'm going to talk about that now. An iterator is a wrapper around a C++ or C pointer, along with that pointer. That wrapper isn't just some trivial syntactic sugar, though. It contains some important information, like where your vector is stored. the iterator tells you whether this is stored on the host or the device, for example, and that matters a lot because a lot of these thrust functions, like the algorithms that I'll describe later and the assignment operator, are overloaded. So you really need those functions to know what device or whether the vector is stored on the host or the device, and the iterator tells you that. So here's a little way to visualize things. So you have, that said though, iterators do act like pointers to a large extent. Not in every the analogy, there are limits to that analogy, but iterators do frequently act like pointers in some of the most basic ways. So just to show you, I'm going to allocate a device vector called dvec. It's going to have 4 elements. And for free, I get dvec begin and dvec end. And here's what's going on. So this figure I took from Jared Holbrook and Nathan Bell's webinar. It was very good, and they explain this too. But I'm going to explain it again here. So dvec consists of the array of these 4 elements, dvec begin and dvec end. Now the pointer in dvec begin points to the beginning, the first element, and the pointer in dvec end points to the element or the storage location just past the last element of dvec. Now you may say, well, if it's called dvec end, why doesn't it point to the last one? Why go one beyond? Well, I don't know for sure, but I think it's because it allows you to take dvec end minus dvec begin, and that arithmetic will tell you the length of the vector, or the number of elements in it. So if, for example, dvec begin points to storage location number 2, and dvec end points to storage location 3, 4, 5, 6, to take the length of the vector, I take 6 minus 2. 6 minus 2 is 4, and sure enough, we have 4 elements here. So that's an advantage to defining dvec end over here instead of over here. Okay? Iterators, like I said before, they act like pointers. So if I allocate a device vector, I can create an iterator that's not necessarily part of that vector, but that points to the beginning of that vector, right? I can copy the contents of dvec begin into this thing that I'm calling begin, and I can do the same thing for end, and I can do pointer arithmetic on it. I can take end minus begin and get the length, like I said before. I can also say something like end is dvec begin plus 3. That's pointer arithmetic. And it just says end points to the element 3 elements down from the beginning one. So in this picture, begin points here, end points here. And you can use iterators like pointers in some important respects. So for example, if I define begin as before, I can set the value pointed to by begin to be 13, for example, and it's the same as saying dvec of 0 is 13. So this is just, I can dereference it like a pointer and do assignment as if it were a pointer. And I can extract values, obviously. I can increment with the just using regular pointer arithmetic. This advances the iterator 1 position, and so on. Now, there are some times when you need to go back and forth between iterators and pointers. Say you've done a bunch of stuff in CUDA-C without using thrust, and you want to convert it into the thrust framework, right? So you want to make your pointer into an iterator so you can use thrust functions on it more easily. So what you can do is, well, first of all, you've got to have a pointer, and you've got to have memory allocated to it. Whoops. And after you do that, you can call this function, this thrust function called device pointer. And it's going to be a pointer to ints, and it's going to be called dev_iter. That's the name. You can name it anything you want. And it's going to get the pointer stored in raw pointer. Okay? So the pointer here is going to get copied into this iterator here, and this iterator is going to have that pointer plus a bunch of other fun stuff. And then I can do these whoops, sorry about the resizing. I don't know what's going on. It's just trackpad and my computer. Anyway, so I can call something like thrust fill, which may say, you know, take the first n elements of this array that's pointed to at the beginning by dev_iter, for example, and I can fill these all with zeros. That just accesses the device memory. The advantage of encapsulating that pointer in an iterator is that I can do this without having to do a CUDA memcopy, or even more cumbersome, make a kernel to access that pointer which points to memory on the GPU. I can just use thrust fill, which is much easier. You can unwrap iterators to extract pointers too. So let's say you do a bunch of things in thrust and think, I need to write my own kernel to do stuff, but I can't pass in an iterator because, look, my kernel's not necessarily going to know what that means. I want to work with raw pointers. Well, you can unwrap iterators to extract the pointers in the same way. So I can call this function thrust raw pointer cast, and I can unwrap this pointer that's stored here, and I can use that. I can store it as an int pointer, and then I can pass it into some kernel that I call. So you have that flexibility. You can go back and forth between iterators and pointers to go back and forth between thrust functions and your own kernels. Now, there are some other iterators that are fancy, that are used as if they were arrays, and you'll see that. So there's this one fancy iterator called a constant iterator, which is a pointer, but with other stuff, right? Iterators don't just have pointers. And some of that other stuff associated with it is some constant. And here's an example of a constant iterator. So after including the proper header file, obviously, I initialize this constant iterator. I'm going to call it first, and it's going to have the value 10. And I can initialize this iterator last, which is just going to have the pointer to 3 beyond first. And what I can do, since a constant iterator has that value associated with it, I can use first as if it were an array. So if I call first of 0, it returns that constant value that I assigned it at the beginning, which returns 10. And in fact, for any index that I give it, it's always going to return 10. This thrust reduce I'll go over later, but that's just summing up all the elements between those pointed to by first and the one pointed to by last. So counting iterator is a pointer with some constant and some offset associated with it. And the upshot of that is you get a sequence for free without taking up much memory. That's what a counting iterator does. So if I initialize a counting iterator of ints with initial value 10, then I get an array of arbitrarily, well, almost arbitrarily large numbers, but without storing all of the that huge array that I would need to store otherwise. So I can reference it as if it were an array, and if I call first of 0, it returns 10. If I call first of 1, it returns the next number in the sequence, which is 11, and so on. For example, first of 100 is 110. A transform iterator is a bit more fancy. So it's a pointer, and instead of just any old value associated with it, the value associated with each iterator at a particular index is going to be a function. So for example, let's say first I remember to include that header. I have a device vector, vec, which has these values, 10, 20, and 30. That's going to be important. I make my transform iterator with thrust transform iterator. I specify the type, that's the int. It's going to be called first, and actually that's the type definition. This is the type. This is what it's called, and then this is the function that actually makes it. That's the constructor. And I pass it in, well, I want to point to the beginning of this vector that I just created, so I'm going to pass in dvec begin, and I want the function associated with it to be the negate function. I'm going to do the same thing for last, and I can reference elements in the following way. So first of 0 is going to return the 0th element of vec, because first points to the same place as vec begin. First of 0 is going to be the first element of 10, but applied, but sent through this function. So the transform iterator transforms the elements of vec and then outputs them. So if I call first of 0, takes 10, negates it, and then returns minus 10. First of 1 is going to return vec 1, which is 20. It's going to negate it, return minus 20, and so on. Permutation iterator is a little bit more complicated. You get a permutation for free. Instead of having to permute a vector and store that whole thing in memory, you can define a permutation iterator, which is much more memory efficient to get the job done. So I'm going to define a device vector called source with these elements in it, and I'm also going to define map, which is a function on the indices of source, which is going to switch things around. It's going to permute them. And then when I make a permutation iterator, this is the type. So in this type definition, I take two index iters, which I defined with type def as device vector iterators. The syntax is kind of complicated with all these type defs, but bear with me. So with the right type definition, which is defined here, I can make pBegin, which is a permutation iterator. Remember, it's made with make permutation iterator. And it's going to point to the beginning of, I'm going to give it the beginning of source. That's the beginning of my actual vector. And I'm going to give it the beginning of the permutation array, the array that defines this permutation here. So, and then when I do these things, I can remember pBegin is a permutation iterator, so I can, since it's an iterator, I can use it as if it were a vector or an array, and I can index it, and when I index it, the values mean the following things. So when I say pBegin of 0, that's the same as saying source of map of 0. So pBegin of 0 is just the value of source, but permuted according to map. So, and that's going to be 40. Similarly, pBegin of 1 is source of map of 1, which happens to be 20. The zip iterator, I'm not really going to go into detail, but it's here in case you're interested. So zip is a feature of languages like Python, which in languages like Python use these data structures called tuples. And a tuple is an ordered collection of objects that aren't necessarily of the same type. And a zip iterator takes two or more collections, or two or more arrays, maybe of different data types, but they've got to be of equal length. And what it does is it combines those arrays element-wise to create a single array of tuples. And here's a bit how that works. So let's say I want a tuple, and they're going to have tuples. At the end, I want a zip iterator, and each tuple is going to have an int, a float, and a char. I'm not going to go over this syntax, but you can check it out online. This is, I need to use these type defs here, and well, I don't need to, but this is a convenient shorthand. I just shorthand the int iterator with the thrust device vector iterator type for ints. And I do the same thing for floats and chars, and those are just all shorthand. These type definitions now mean these things here. And I do that because I want to define a tuple type with an int, a float, and a char, and call that an iterator tuple. So now I've created this type called an iterator tuple, and I want to create a zip iterator of that type. And so what I do is first I make the type def for the actual zip iterator. This is the type def for the tuple. To create the type def for the zip iterator, I say type def thrust zip iterator, and I pass in the type def for the tuple that I want. That's the basic data type for the zip iterator. And I name this data type as follows. And now I actually create the iterator. So it's going to have type zip iterator. Its name is going to be iter. That's the name of the object. And I'm going to call thrust make tuple. And this is actually going to zip these things together. It's going to combine these three arrays, or the arrays pointed to by each of these iterators, and it's going to take all the first elements, make that into a tuple, all the second elements, make that into a tuple, and so on. And now I can reference these things as follows. So if I say iter of 0, it's going to return this first tuple, which is consisting of an int, a float, and a char. And same thing for the other three. Now if I want individual elements of those things, I can use this function get in thrust. And for example, this function, this call here gets the 0th element of the second tuple. So that's equivalent to going to this tuple and getting the 0th element out here, and that returns 2. A note on containers. So a container is the generalization of a vector. So it's a storage class used by the standard template library, or STL, and thrust as well. And there are many, many more containers than vectors. These are just some examples of the containers that the standard template library has. Thrust does not have nearly as many. The only container that I use personally are vectors. I don't know if there are more, but standard template library has many, many more. Still, thrust has the advantage of being GPU accelerated. And I'll flesh that out a little bit more when we get to the algorithms portion later. But needless to say, you get a lot of other containers in STL. Fortunately, thrust is built so that it can interface with STL very well, even if you use STL and these other data types. So if I have, for example, a list here, if I'm using STL and I create a list, and I created with elements 10, 20, 30, and 40, I can turn that really easily into a device vector. So I can create a device vector of ints, and I can call it D. And I can copy all of the elements in that list into D from the host to the device. Even though this is a list, this still works, which is really cool. You can combine, all sorts of different. You can use all sorts of different data types at once, and you can still use thrust. All right, algorithms. This is the really cool portion. Now, I just showed you code playing around, seeing how this stuff works. Algorithms are most of the GPU accelerated portion of thrust. They are the power of thrust. They are why you want to use thrust instead of STL when you're doing things fast. So there's a lot of cool algorithms. I'm going to go over them a little bit. A transformation is sort of a generic term for applying the function to every element within a range of a vector. So for you R language users out there, a transformation is equivalent to vectorized functions in R. if you've heard of vectorized functions, or if you're working with a matrix, let's say the analog would be apply over a matrix. But since we're dealing with linear arrays, it's easier to think about vectorized functions, and those are kind of like your transformations and thrust. So here are some examples. There's fill, sequence, replace, and transform, which are basically what they sound like. I've already gone over thrust sequence and thrust fill, so I'm not going to talk about them. Well, I'll mention them right now. So first of all, I've got three device vectors just for demonstration. They all have 10 elements. They're named x, y, and z. Thrust sequence takes the elements inside x from here to here, gives them each the sequence of number 0 from 0 to how many there are. Thrust transform is really powerful because what you can do is, for example, I can compute y equals minus x like this. I can just take the elements that I want from x, I negate them with this function that I pass into it, and I store all those elements in y beginning at y.begin. Okay? So it takes all these elements, negates them, stores them in y from the beginning to however many there were in x to copy over from x begin to x end. Now, the negate function is explicitly passed in as this fourth argument here. And what you can do is you can create your own functions and pass them in and use transformations on them. So, for example, if I wanted to pass in a modulus function, I could do that here. So I can do the same thing. I can take these elements of x, store them in z, and oh yeah, I can take these, I can store them in y. I don't think the z begin should be here. Yeah, I don't think it should be there. But anyway, I can take these elements in x, I can take the modulus function, which default is going to take, I do need z begin. Because z begin, I'm going to fill it with all 2's. So from z begin to z end, this all gets 2. So the value pointed to by z begin is going to be 2. And so what I'm going to do is I'm going to take these values, I'm going to store them, I'm going to take them and compute the modulus of that. I'm going to compute x mod 2, and I'm going to store all those values in y. So you can imagine you can pass in pretty much any function you want to the transform iterator as long as you define it correctly. And the webinar by Bell and Holbrook explained how to do this very well. I'm not going to go over it. I'm pretty rusty on that part of C++, sort of advanced C++, defining your own classes. But needless to say, you can create any function you want as long as you do it right. I would refer to that tutorial for how to do it. It's very powerful because the transform iterator applies this transformation in parallel to the elements of your vector if it's on the device. And here's the output, which is the correct output. You can verify it yourself. All this code's online. Here's how to compile this code, for example, and you can refer to the makefile online. A reduction, one of my favorites. If you're writing a Markov chain Monte Carlo program, like I sometimes do, my research, I need to sometimes compute sums of all parameter estimates or products of all the parameter estimates that are kind of sort of like sufficient statistics for other distributions to make things easier to compute. And I use reductions to do this. I use parallel reduction specifically. So a reduction is an algorithm that applies a binary operation to an array of things and outputs a single scalar. And the pairwise sum is the canonical example. And there are many ways to write it. The simplest way is this one. So int sum is my output, and my function is thrust reduce, and I apply thrust reduce on dvec begin to dvec end, and it takes all the elements from dvec begin to dvec end and sums them up in parallel. And it does that pairwise sum for you. And I think that's pretty darn cool, because in previous lectures I went through great length to define the pairwise sum and how to implement it, and how to think about it, and it's really easy to mess up, and I can only write it out in a pedagogically friendly way by having restricting my arrays to powers of 2, and there are all these messy little issues that you might have to worry about. Thrust reduce just does it in one line, which is really convenient. I use this all the time, and it's pretty amazing. You can also, but thrust reduce is much more flexible than just the regular pairwise sum that you can think of. So I can also pass in an offset of 0. For example, this is where it's the pairwise sum starts out at. I can also, in this fourth argument, pass in that binary operator that I want to use. So for pairwise sum, I would use thrust plus. If I wanted to use pairwise product, I would pass in a product function here, and it would compute the pairwise product. There are also, like I said, these are what those third and fourth arguments do. I can use other reductions too. So thrust count is syntactic sugar for thrust reduce, but with the fourth argument as a counting function. So I can count the number of times a value appears in the vector, and this is sort of a different, different kind of reduction than sums, products, what have you. So here's how it works. So let's say I have a vector of 5 elements. Some of them are going to be 0. Some of them are going to be 1. In fact, I have 3 1s. And thrust count is going to count the number of 1s. And it's going to begin at the beginning and end at the end, because I passed in the corresponding iterators. And it's going to count the number of 1s, because 1 is in my third argument. And the result is 3. Now there are also scans, and a scan is also called a prefix sum, and it's basically a sequence of partial reductions. So for pairwise sum, for the sum operator, a scan on an array or a vector is going to be a sequence of partial sums. Here's an example. So let's say I have data that looks like this. I can do an inclusive scan, which is a kind of scan, on this vector data from beginning to end. I'm going to store the results back into the data at the beginning. An inclusive scan is also called an in-place scan, by the way, because this is what it does. It takes the first element of data, stores back in the first element, takes the original first 2 elements of the data, stores it here in the second element, or 1th element of the data, takes the original 3 elements of the data, does a pairwise sum on them, sums them up, a parallel pairwise sum, puts them in data 2, and so on. So you have a sequence of partial sums all the way until the last one, which is the pairwise sum of everything. There are exclusive scans, which, and this code is almost the same, except I use exclusive scan, and now my final array is going to look like this. So it's just going to be offset by a little bit. So it's going to start it at 0 and then keep going, and then the last is going to have everything summed up except the last original element. And that's the difference. I usually would want to use an inclusive scan. You might want to use an exclusive scan, but I don't see as much of a use for it, personally. So there are also parallel reordering algorithms as well. And partitioning and subsetting, not subletting. Why did I say subletting here? That's subsetting. Darn spell check. Anyway, so there are a bunch of reordering functions and copying functions. So there's copy if. So it's exactly what it sounds like. You pass it in a couple of iterators. You pass it in a logical function, and if that logical for every element that logical function returns as true, you copy that element over to some other place. Partition is a reordering according to a logical function such that all the true elements are returned first and then all the false elements. I'll explain what I mean in a minute. Thrust remove and remove if are exactly what they sound like. You remove if, for example. You pass it in a vector and you pass in a logical function, and it removes all the elements that return false. And thrust unique is exactly like the unique function, the function unique in the R language. For those of you who are statisticians like me, it removes duplicates in a vector. So here's an example of the partition. So I have this isEven function, and this is the sort of function that you would pass into a thrust function. And this is sort of the way that you might initialize that. There's a lot syntactically going on here. It's a struct. You can also create them as classes. I'm not going to go over this, but basically, if the number is even, x modulo 2 is true, this is going to return, this is saying I'm going to return true or 1 equivalently if x is even, otherwise I'm going to return 0 or false. So I'm going to use this function isEven in the code. And how it works is the following. So here's my main function, and A is going to be this array from 1 to 10. By the way, I can use host arrays directly, like A, in these functions, but they're not going to be GPU accelerated. If I want to use GPU acceleration, though, I've got to turn these device vectors into iterator. I got to convert my data into device vectors and or iterators before I use thrust. But here's an example. Just I thought I'd throw a host vector in, a host array in here, just to tell you that if you're working on the host, I mean, you're not going to have GPU GPU accelerated stuff, but it's still going to work. So anyway, n is just the number of elements. When I call thrust partition on this array, it's going to take all the even numbers and put them first, and it's going to take all the odd numbers and put them later. I know the odd numbers are ordered in this weird way. That's what I got when I ran it. I don't know, you may get a different ordering if you run it, but in any case, I don't know why it's doing that, but it's putting all the even numbers first and all the odd numbers last, which is what I wanted. I have a sort algorithm, so I can take this array and I can call thrust sort on it, and now I get a sorted array. Pretty simple. There's also sort by key, which is a concept that you see a lot in Python, because Python has this dictionary structure for the dictionary data type natively, and what it does is you got a collection of values and a collection of keys, and you sort the values according to the keys. So for example, if I have an array of keys and if I have an array of values, and each value corresponds to its key in the same location in the other array, for example, the value corresponding to key 1 is A, the value corresponding to key 4 is B. I can sort by key. I can call thrust sort by key on keys and values. And what that'll do is that'll take the keys and values and it'll sort them both in the same way, and it's going to sort them so that the keys go from decreasing order to increasing, from smallest to largest. So the keys are now sorted, and the values are permuted accordingly. There's also stable sort, and notice I can pass in any sorting criterion I want in this third argument. So thrust greater is, it just specifies that I want to sort from largest to smallest in the stable sort. Okay, this is what I went over. Thanks for listening. And just really quickly, this tutorial online is much better than the talk I put together. I just wanted to get this talk out there to complete the series and give my 2 cents from a statistician's perspective. Oh yeah, we've got this is the C++ book I mentioned by Walter Savage. I highly recommend it. Like I said, I read it from cover to cover when I was an undergrad. It helped me immensely with understanding C++. And there is also a Thrust documentation, this quick start guide that you should check out if you're starting with Thrust. Here's the code from today. Well, the code from today is posted on this course's webpage. I'll get the video uploaded too. When I gave this talk in person, well, I don't know what went wrong with the audio, but it's going to be up for real this time. Materials for all of the series are available here, and I will see you next time.